Okay, welcome back, my dear students. This is lecture 38. I'm Dr. Kamran, the instructor of this course. Uh, Today we are going to discuss the same treatment for the linear PDEs using the domain decomposition method. And if you look at the previous lecture, in previous lecture we uh, investigate the linear PDEs using the ADM method, and the operator in that ADM method was used in terms of time variables, and the x dimension or the space variables are supposed to be constant in the previous example. So it is important to point out that this method was used in the previous examples in the previous lecture, uh, in the t dimension by using the operational operator LT, and for this differential operator we choose the inverse operator L of t power minus 1. But here in this lecture, uh, we are trying to change this linear operator, this linear differential operator, and the inverse operator, and that is exactly the differential operator L of x uh, in the x direction, and the inverse linear operator for this differential operator here in this example is Lx uh, Lx power minus 1. You have, because this is second order derivative, so it must be Lx and x, because the the linear terms in the x variable is second derivative. So we are going to use uh, the linear operator like in this form: partial square by partial x square. So this is exactly the linear operator in this example, and we are going to calculate the this example, uh, this heat equation using this linear operator. And for this linear operator we have the inverse linear operator, which is you can say the double integral of the function ux of t dx, and because the change occur in x direction or in x coordinate. So this is the space variable or the space coordinates. So this is the invertible operator for the above linear operator. Now the example is this one. We have a heat equation u of t, or partial u by partial t, is equal to partial square u by partial x square, where x is in between 0 and pi and t is greater than 0, and one boundary condition is this one: u of 0 of t is equal to 0 at at 0 surface, or when x was 0. This is one boundary condition, and t is greater than or equal to 0. And when x is equal to pi, this is exactly, if for example if this is a horizontal line. So for this horizontal line, uh, when x is 0, this is one extreme, and when x is pi, this is another extreme for that x. So between these values we have these two boundary conditions: u of 0 of t is equal to 0, exactly here, and u of pi of t, we have exactly this boundary condition. So you can see here, this is exactly the boundary condition for this problem, and u of x of 0 is equal to sine x when t is 0. So this is exactly the function value. The curve is exactly, you can say here, you can see here that this is exactly the curve or the f of x. So between this curve or for this x we have these two boundary conditions, and this is a homogeneous linear PDE. So now we have this heat equation, and for this heat equations we are going to choose the linear operator L of x of u of xt is equal to L of t of u of xt, where x is in between 0 and pi and t is greater than 0. So this is the operator form of the above equation, of this equation. This is exactly the operator form of that above equation. Now, as we discussed before, that here in this example we are going to choose the linear operator L of x is equal to this one. This is exactly the linear operator, and which is in terms of x direction, or which is in terms of x space variable. And for this linear operator we assume that this is invertible, this linear operator is invertible, and uh, it is defined as L of x power minus 1 of the unknown variable is equal to the integral from 0 to x, second integral from 0 to x, the unknown function, and the differential of the space variable dx and dx. So this is exactly the operator form, or the operator, the linear operator, and this is the invertible operator for the above linear operator. Now the next step is an a domain decomposition method, that we are going to apply this invertible operator on both sides of this equation, this equation 3.38. So once we apply this invertible operator on both sides of the above equation, then this equation reduced to exactly this form: L of x power minus 1 L of xu, where u is a function of xt, is equal to u of xt minus uh, u of 0 of t minus x u of x into 0 t is equal to u of x of t minus x into ux of 0 t. So here this boundary is 0, so it vanished, and this value is equal to the x u of x of 0 t, exactly this value, and this is, you can say, this is the zeroth order solution. We can also call this zeroth order solution. And after that, we are applying the again the linear operator in an above equation. So once you apply, you have this u of x t is equal to the zeroth order solution plus lx minus 1 into this value L of t of u of x t. So this is now exactly the uh, another form of that above equation. So uh, and this can be reduced to this one: u of x of 0 to is exactly is a function, h of is a dummy function, and this dummy function is equal to this u of x to. We just call this is h of t. And the next step in this method is to reduce this above equation or transform this above equation in a series form, and where u of xt is equal to summation. This is exactly we are choosing this u of xt in this form. U of xt is equal to summation. This is summation sign where starts from 0 and ends at infinity. U n of xt. So we choose this series, and now uh, we are going to replace ux of t in this above equation by this series. So once we replace this ux of t by this series form, we have then this general form for the above equation, and this is called the series form, which can be calculated in each segment. And this series can be written if you expand this series. So this is u naught of xt plus u1 of xt plus u2 of xt plus u3 of xt and so on. And here we will have u0 of xt, u1 of xt, u3 of xt and so on. So for u0 of xt we have this solution. This is zeroth order solution. And for u1 of xt you have here u naught of xt, and once you integrate this, two times integrate this zeroth order solution, you will get this u1 of xt. And similarly, when you want to calculate this u2 of xt, you need to integrate this value two times then you will have the solution of this u of ut of xt. So once you have all these segments, the solution of all these segments, plug in all these values in this equation 3.44 uh, again, then you will have exactly this form. Now this is exactly the general solution for the above PDEs, where h of x is h of t is equal to u naught of xt. So this is exactly the general form, this one. Once you calculate or simplify the above equation, so this will be now the uh, general form or the general solution for the above PDEs. Here in example 4, the same treatment with the previous example, but here again uh, the linear operator is L of x and the invertible operator is L inverse of x. So you need to calculate this example as well, the solution as well, the same treatment, the same process, the same investigation, but the calculation is a bit different because of boundary conditions, because we have some different boundary condition in this example. So that's why the solution must be a bit different from the above example. So this is your homework. Try to calculate each and every step of this example, and if you have any problem, then you can ask from me. And this is another example, example 5. This is again your homework. So the process is exactly the same, but slightly we are changing the boundary condition in the original PDE. The remaining process is exactly the same. Okay, so try to calculate these sort of examples. Thank you.